Before we get started, I just want to, express to all you the support that I received while I was CEO of Lightwave Logic. I can't tell you enough how excited I am at where we are right now, the momentum we've built, and everybody in this room I know has just been tremendous to me. I'm really pleased that I've been allowed to continue on as the chairman. The board, approved that, as all of you know, and you saw in one of our PRs. And it means a lot to me because I'm fully vested in this thing. I believe in it. We have probably one of the best boards that exists in this market, and I mean that sincerely. It's been a real honor to serve as the CEO, but love the fact that I'm staying on as chairman. The other thing that I want to do, this is the first time that we've also had all of our employees actually present here, and they're the reason that this is, being so successful. We have our chemists, our device people. We even have a new employee just started yesterday sitting in this room. Okay, we are gathering just the most unbelievable group of people that you as shareholders could ever want. Okay. I'm amazed at the talent that we're starting to attract, and it's really important, for the company and for our progress. So if the employees wouldn't mind standing up, because these are the guys making it happen, and I think they deserve a hand. So, all right. With that, I will turn it over to Michael Levy, and he's got a great presentation to kind of take you through all the things that we're doing and what it means to the market. So, Michael, over to you, sir.
Okay, we're working. I have to take a drink in case I lose my voice. Well, good morning. I'm going to spend probably the next hour going through a set of slides, and I've actually put the slide deck together in a form that hopefully everybody will at least understand some of the technology. So I'm not going to go into any detailed equations or anything like that. So this is not going to be one of those lectures. Let's see if this thing works. I'll go back. So what I'm going to talk about today is high-performance polymer photonics for next-generation PICs. And so, in case folks don't know what a PIC is, that stands for a photonic integrated circuit. And a photonic integrated circuit is more than one photonic device in a chip. So it's a discrete photonic device is a device on its own, and an integrated circuit is more than one device. So we'll be using that term quite a bit. All right, so that's, so I have to put this slide up, the safe harbor slide. I'm going to go through this, and this is the agenda. We're going to do an introduction, going to give you a tutorial on the technology. Then we're going to talk a little bit about the environment and the markets. And then we'll go on to polymer photonics as a PIC platform, and then look at some of the integrated photonic applications. The one that we're focused on right now is data centers, but as I'll show, we can see some medical and consumer opportunities as well. And then I'll close. But the main thing from this talk, you'll see at the bottom of each slide, this big green bar. And the big green bar is a takeaway. And so if you feel that the details on the slide are too technical, the green bar at the bottom is the very simple perspective of what's said in the slide. So if you want to focus on something in the slide, it's generally the green bar at the bottom. So, 100 years ago, Alexander Bell, known as Professor Bell, that's where Bell Labs comes from, Bell Northern, had the photophone. In the 1880s, he used, according to the New York Times that I found here, sunbeams. And so he conveyed photos from one unit, a transmitter, on this side, to a receiver on another side. I don't fully understand the technology he's using in these pictures. But, the question is, if you look at the takeaway at the bottom, I mean, was he lucky or visionary? Was he even clairvoyant? And I'll address that question as we go through these slides. So let's go through to more of a tutorial on the fiber optics. So back in 1870, this guy called John Tyndall is Scottish, fellow of the Royal Society in London, gave a presentation. And what he showed was a bucket of water and a sun shining into the bucket of water and the water coming out and actually turning the corner and going into a pail at the bottom. And what he actually demonstrated was the first time in total internal reflection. That's light, sunlight going into the water and actually turning the corner and keeping to that water. And that was the first real demonstration of light turning a corner with internal reflection. In fact, when I looked at that and I started going into, wow, this guy's pretty cool, I actually realized it was published by this Swiss physicist called Colorado back in 1842, and all Tyndall did was repeat the experiment. So he didn't actually invent it, he actually demonstrated it, but it actually was invented by a Swiss guy, I guess a long time ago. But the concept of internal reflection is what we're using in our technology today, and I'll explain that. And internal reflection is what you use in fiber optics. So here's a real example of a red laser going into some fiber, and you can see the fibers lit up. And the light can go around and around in circles. And so we use fiber optics to communicate today. And we've got communication signals pretty much the size of a human hair. And this is not a new technology. It's been around a long time. The concept, as I've just shown, is 100 years old. And it's been used commercially since the 1980s. So it's been here for about 40 years. And this is what a sort of fiber optic looks like. If you look at a wasp at one end and you turn the corner, you'll see the face at the other end. So light can actually turn around corners just like we're showing here. So it's the takeaway of this slide, it's internet via glass because it's glass-based. Now, fiber optics is the most least expensive, most reliable method for high-speed and long-distance communications. And we can see here, this is an AT&T photograph from the 1970s when they were first starting putting fiber optics in the network. This is copper cables. And I believe this photograph is supposed to represent all the data in these copper cables goes into this one fiber strand. So this was their promotional photograph. So it's economic to use glass, and since the 1970s, it's everywhere today. In fact, it's all over the country. So fiber really connects us all together. And you can see from San Francisco to New York. I mean, this is just a map showing all the connections, a few photographs down there. But the whole country is literally wired. In fact, if some of you are really lucky, it actually goes to your house, like the Verizon Fios they have in the East Coast. In fact, if you look at this, it's not just the country. The whole world is wired by fiber today. This is fiber optics under the oceans, under the seas, under the ice and the poles. So it's going all over the place. So we're seeing fiber everywhere. And in fact, if you think about it, it's the most least expensive, most reliable method for high-speed communications. And while we already transmit signals at really high data rates, like 100 gigabits per second, we really only started to utilize the potential of this. So yes, it's been around for 40 years, but it's still growing in potential and in speed. So it's very economic to use glass. And if you look out where you live, you might see these big rolls. These are big rolls of fiber optics they're putting into the ground. That's outside plants. And if you look inside data center type buildings, you'll see racks of faceplates. These yellow wires are single mode fiber. These orange wires are multi-mode fiber. There's installations everywhere today. So it's actually pretty exciting to see it everywhere. And how small really is it? Well, I don't have any hair, but it's about, go back, it's 62 microns, which is pretty small. And that's the human hair width. So fiber is, the core of fiber is 10 microns. That's pretty tiny. And the outside part of the glass is 125 microns there. So that's about double the size of a human hair. So it's slightly bigger than human hair, but it's pretty small. And so this slide is interesting. I tried to put this slide to really explain what Tyndall showed in his experiment. And it's sort of an experiment you can do for yourself if you wish. If you put a pencil in a glass of water, you see that the pencil doesn't actually look straight. It sort of bends a little bit when it hits the water. Well, that's because the refractive index of water is 1.3. It's a denser medium than air. So if you're looking for fish in a fish tank, you may see the fish, but if you try and spear it, you're not going to hit it because you're going to actually miss the fish, right? I never actually tried that, of course. But if you look at it from the physics standpoint, what I've done here is it's this internal angle of reflection. If you imagine you're sitting in water and you're looking up, And I found this photograph on the internet. You're looking up from the bottom of the swimming pool, you can see out. And this photograph shows you can see the lights at the top of the water. So you look straight up, or nearly straight up, you can see right out. But if you look along the horizon, you're sitting on the bottom of the swimming pool, like this guy here. If you look along the horizon, down at the end of the swimming pool, what you see is reflection of the lines in the surface. And so what's actually happening is what this graph showing here. You're seeing the light bounce off that boundary, that reflection surface then going back down again. That's internal reflection. So if you go swim next time and you sit in the bottom of the pool, you can just actually see that. So that's optical internal reflection. And in fact, I mean, if you go scuba diving or snorkeling and you look at a turtle, the same thing happens. You're in the water, you look at the surface, and you can see the reflection of the turtle on that interface between the water and the air. That's total internal reflection in the water. And this is the concept we use in fiber optics. And so we set up the condition in a glass fiber with a refractive index a little higher in the core, so we send in 1 zeros, 1 zeros, which is your digital data rates, and you keep the light to the center. And that's how you can conduct the light all the way across the country. It's a real simple concept. So keeping optics in the fiber with integrity at destinations. You put in a nice square wave, and you really would like a nice square wave on the output. So that's what you design systems for. And that's how we use the glass. In fact, there's different types of fibers. The one at the top is a multimode one that goes typically a few hundred meters. That's a step index. The next one down is a gradient index. That's changing the conditions of the glass. That's a little bit further. But the ones that are used across the country, the ones that I showed that are yellow in those racks, the ones that we are using, is a single mode fiber. These are the ones that go 10 kilometers, 100 kilometers, 1,000 kilometers. So this is the technology we're using. Lightwave is using single mode fiber. We're not making fibers, but we're using the fiber-based technology. So, in terms of the wavelength of light, because we have to think about what wavelength of light we put down the fiber. Now we're human, so we got the visible range here, so we can see from purple all the way to red, the rainbow colors. And that wavelength range is 400 nanometers to about 700. What I put on here is cats can see UV. They can go down to about 250, 300, because we know cats can see in the dark and stuff. And snakes can see infrared in the heat. So they got a little bit broader optical spectrum than what we have. But the wavelengths we use in fiber optics are these two here, 1310 and 1550. These are infrared wavelengths. So fiber optic systems transmit using infrared light, invisible to the human eye, because it goes further into the optical fiber at those wavelengths. So that's what's designed. I mean, the glass has nice absorption minima at those wavelengths, and that's what we designed to use. 1310 is typically the wavelengths you see in data centers and short distance interconnects, and 1550 is what's used in the big telephone networks across the country and under the oceans. But these are the wavelengths we're going to be involved with. Okay, so let's talk a little bit about optoelectronics. Optoelectronics is an interesting word. I mean, it's optics and it's electronics. Now, everybody knows the silicon IC chip has been around for 60 years, and that's your electronics over here. There's an Intel chip over there I've just shown. And optics is dealing with light on the right-hand side. And optoelectronics is actually the combination of the two. So you're controlling optics using electronic control. And sometimes we call it optoelectronics. Certainly when I got my PhD, we called it optoelectronics because everything was used that word. But today folks have used this, coined the term photonics. So it essentially means the same. And so they're interchangeable. Optics and photonics seems to be used similar today. And so we're in the field of photonics or optoelectronics. So, typical devices that you find in the optoelectronics field. I think everybody's seen the LEDs in traffic lights. I mean, these are green LEDs. You can see the individual LEDs. We've all seen solar cells on roofs of houses and things, right? Corning makes a lot of the optical fiber. In fact, some of us, if you've broken apart DVD players, Blu-ray DVD players, you'll see blue lasers. So that's used in optical storage. Photodiodes are used in communications as well as telecommunication lasers. So the reason I bring these is because these types of devices are used in the fiber optics field. And so these are the ones that we'll be working with. These are typical optoelectronic devices. Now, if you think about these for a second, these are what we call discrete devices. These are not integrated. This is one device in a package, one device in a can. This is one laser in a butterfly package. So this is not integrated at all. This is not photonics integration. These are discrete, single optoelectronic packages. Now, to go to the next slide, it shows you, and I've given you some examples of discrete optoelectronic devices, including some ICs. So you've got some modulators here and some lasers and amplifiers, splitter combiners. But what a PIC is, a photonic integrated circuit, is taking some of these devices and integrating them in an even smaller package. So you're basically shoehorning discrete optoelectronic devices into a smaller box. And the way you do that is you're going to have to integrate them on a chip. You have to get them closer together. And this is what we're all about, is how do you get some of these things, which are quite large, shoehorned into a smaller box. That's a photonic integrated circuit. So PICs are the equivalent to many components, and so they give you functionality. So if you've got different types of lasers and modulators on a chip, you can do different things, lots of different things. So it gives you that versatility. A typical simplistic architecture, this is a photonic integrated circuit. A photonic integrated circuit could be a chip this size. On the chip you'll have 4 lasers. Each laser has a different wavelength of light, which I've shown with a different color. Laser will be connected to a modulator. The modulator is used for high-speed signaling. One way of looking at this is like your eyelid. A modulator will open and close and get a very nice square waveform. So it doesn't matter how good the laser is, but the modulator nicely cleans up the signal. This is a box we typically call in the business a mux, or a multiplier, and that will actually multiply all these signals together and put them down the fiber. The reason I've colored the fiber in a rainbow color is because that fiber has 4 different wavelengths all going down the same fiber. So we can do that. We can have 4 different signals going down the same fiber. But a PIC is actually, for example, a transmit PIC will be this type of structure on a simplistic format. So a typical PIC transmitter layout showing where the modulators fit. And so if you look into the literature today, there's been obviously a lot of optoelectronic components. If you look at them in the chip form, this is what a modulator looks like in lithium niobate. This is a typical laser diode, what it looks like in indium phosphide. This is this is like a silicon photodetector, and it looks like we have an indium phosphide-based semiconductor optical amplifier. These are all known as active devices. Active means that they're either sending light or they're receiving light. And so these are typical what you would see in fiber communications. So, one of the questions is you've seen from our press releases, we use modulators. So why do we want to use modulators? Well, if you directly modulate or you directly power on a laser, it can only go so fast. Lasers sort of are limited by the way you modulate them. And so in order to get the system to go even faster, you put a modulator on the outside of a laser, and it cleans up the signal. If you can do that, the signal can go further in the fiber, and it can go faster. And even as you've seen from our press releases, we want to go a lot faster. We're going to have to use modulators to get to these high-speed numbers. So modulators, from the takeaway at the bottom, provide high-speed performance and distance. This is why we're using them. And this just shows you what the modulator function is. Just a standard Mach-Zehnder modulator. But really, here's the laser diode. You put in the 1010 data into the modulator, you get a nice, clean, square waveform out. And so modulators are actually critical if we want to address these types of speeds in the fiber optics today. These are very high-level speeds. I'll explain that in a second. But as you go up to these speeds, you can't just do it with the laser diode. You have to have the modulator in front. So the important piece of the tool in these systems, and if you look at a typical optical link you'd find in these networks, CW laser on the left, the modulator is this box in red. You put in the 1 zeros at the top, you get nice clean signals out, goes through loops and loops of fiber, you receive the signal, and you've got the we received 1010 at the other end. And so simply modulating lasers limits the speed performance. What we say is external modulators, because they're sort of external to the laser. That's what we use in the industry. They actually clean up the signal, and they provide high-integrity signals across these links. So they're an important piece of the pie. And so if you can do modulators and you can do waveguides, what I've ringed here is the rib or the ridge. So we're working on this now with our modulator design, and we're working on the Mach-Zehnder design. But you can see this is from a textbook. It's from UCSB. You can see there's other designs you can do too. So once you can do one, you have a lot of other opportunities and other designs. So we're just focusing on one right now, just so that we can get this technology to market. But there's other opportunities too. What we call these are passive waveguide architectures. They're ideal for polymers. So we're not just limited to a Mach-Zehnder design. We can do other ones too. In fact, one of the issues you'll find if you've been in the industry a long time is how do you not lose light? It's very easy to lose light. Light can escape in many different ways. And so coupling light in and out of the waveguides, either from LEDs or laser diodes or through lenses to fibers, is really, really important. And I put this slide up to show that the optical coupling part of it to light waveguides is a critical skill. So you look at all the folks in the industry today that deal with light, they really have really good knowledge of how to make this very efficient, and so you don't lose light when you go from a modulated device to a fiber. And this is a metric that we have to carefully watch and improve our skills. In terms of communications, if you look around the home, you've seen copper wire. I think most folks have seen copper wire connected to things like computers and different interconnects. We've also seen twisted wire pair. Here's the copper wire. Here's the twisted wire pair. I think folks have seen different types of twisted wire pair that goes a little faster. Our old modems use DSL, which is twisted wire pair copper, when we had the old modems connected to our computers. Now we're seeing a lot of fiber optics come into play, which gives you the higher speeds. And this is really what's driving this. Optical fiber allows the higher speeds to go longer distances. So yes, we're seeing copper around, but eventually it's going to be replaced with fiber optics. And in fact, the thing that you have to think about is it's like a pipe of water. The larger the water pipe, the more water can flow. It's no different with data. The larger the channel, the larger the pipe, the more data can get through. And right now, the use of us using YouTube and videos, we just want bigger pipes. So depending on what we connect, whether it's through the lampposts or through the houses and the computers or different systems, we just want bigger pipes. We want to actually do more videos and use more data. So larger optical channels allow much more data to go through the system. And in fact, it's not just locally, it's across the country, and it's connecting all sorts of different types of products like laptops and cars with their GPS. And so optical fiber connects many consumer components today. And that's what's really changed over the last couple of decades. So let's talk a quick view of the environment. Some of the folks here have seen these slides before, but they're good because they give you a good idea of what the environment is doing. Before, we had a lot of computer-centric type situations where folks with computers and big mainframes. And today we're doing a lot of stuff in the cloud. It's certainly network-centric. But what's the future going to look like? Oops. It's going to be user-centric. We're going to do a lot of cloud access. In fact, I'm already doing a lot of cloud access. I'm using cloud to save a lot of data today. And we're going to go from exchanges, which are old telephone exchange buildings that switched all the telephones, to data centers, to huge data centers. But what this slide is talking about is the network is a catalyst for change in our lifestyle. Our lifestyle has changed. I mean, everybody carries, a smartphone. Everybody does some, Skyping or video texting, and we're going on the internet at any time. So it's really changed our lifestyle. And our lifestyle has evolved through the heavy use of data and traffic. And whether this graph is true or not, this comes from the Japanese talking about body area networks and personal area networks. I'm not sure if that's true, but what is true is the environment is changing, and we're using a lot more data. And we have new traffic patterns. Now, this is, you can talk to the data center guys, you know, the Facebooks and the Googles and the Microsofts, and they'll talk about architectures and the data center fabric. A fabric is their architecture. And the biggest thing that's happening in these places is it's evolving very, very quickly. The growth of the traffic, the video traffic, is forcing these guys to change their architectures every year or every couple of years. And so they've gone from what they call legacy multi-tier architectures, where a lot of the traffic is north-south and not much of it's going east-west. And now they've changed it to a lot of it going east-west. I'm not an architecture expert, but this is what they're designing today. And they're all trying to figure how to go to traffic that they call it omniflow. It just connects everything to everything. And this is really difficult to design, but this is the goal of these type of data center guys, to have everybody connected to everybody. So it eases all the traffic problems so we don't get traffic jams, just like we do when we're driving in I-25 in Denver, right, in the rain. So the same thing in data centers, you just don't want traffic jams. But the takeaway of the slide is all this has been driven by huge growth of internet bandwidth. Now, whether this number of 78% is right, I've seen all sorts of numbers. This is a 2016 number. But the point is the growth is so big, it's actually forcing the data center guys to rethink their architectures. So, you know, was this guy right? Was he lucky? But what he's actually showing, if you really think about it, he's showing data flow from the transmitter or the photophone in 1880 to the receiver. So maybe he was really lucky. Maybe he got it right. Maybe we should have invested in this guy back then. But if you think about the photophone, right, I put it up there, photophone is really video. I mean, that's what this guy was talking about 100 years ago, right, or 140 years ago. If you look at, this is I got this data from Cisco. It's called the VNI, the Virtual Networking Index. And it shows you the amount of traffic that's going on. This is IP traffic. This is the traffic in the internet, all of the traffic. And the majority of that traffic is that dark blue color. That's video. So maybe Professor Bell was correct, right? It's video, right? This is where we're using the traffic today. And this is, what, 2015, and I've just forecasted out to 2020. So this is right off their website as of a few days ago. But here's the interesting thing, if you look at this graph, yeah, there's lots of video, but what's this metric, exabytes? Exabytes is something that none of us are really aware of, right? So let's try and explain that. Well, we know what kilo is, that's 1,000. And if you remember the old telephone system we had, that was 6 kilobits per second. So that was the speed of your telephone signal 30 years ago, 6 kilobits. So that's 6,000 bits per second. So that's that range. Today, most of us have got some type of 10 megabits or 50 megabits to the home. So that's a million, right? So that's mega. And giga is what data center guys are using for their parts. That's 10 to the 9. Giga is basically a billion, 1,000 million. So it's 1 0, 1 and 9 zeros. And then I'm going to look at in a minute the front plates of some of the servers in the data centers. And those guys are talking 1,000 even higher. They're talking about terabits. That's 10 to the 12. That's a billion, right? And then when you start looking at traffic, you start measuring aggregated traffic in the network, you start getting to peta and exa. Peta is 10 to the 15. That graph over there is 1 with 18 zeros behind it. That's the traffic. And they're talking about 200 exabytes. I think that's 200 up there. And if you look on the Cisco website, they're talking about the era of the yottabyte, which is the next generation. So as soon as that gets to 1,000, now we got, the zettabyte, which comes next. I mean, it's amazing. I've never used these terms before. But this is what's happening. So the takeaway is, I think old Professor Bell and his photophone was probably correct here. So if you look at where it's all happening, lots of bandwidth, lots of growth. I mean, these numbers of 23% cloud traffic growth, 44%. I mean, these metrics are looking good. It just means that our kids are using data more and more, and I have to watch my phone bill. I mean, it's classic, right? In the 1960s, I was a kid, and I got taken to a telephone exchange in London. These are large buildings that look like this. And they have all these racks of mechanical switches They actually were called Strauder switches. He was the guy who invented it. It was like crickets. I mean, all clicking of these switches as it actually switched all the telephone calls. And these are large buildings. But if you look today, I mean, these are Google photographs. This is the inside of Google's data centers. And you can see those yellow fibers. They're the fiber optics on these faceplates. You can see it just goes on and on and on. I mean, they have motorized vehicles in these places because they're so big. In fact, how big are they? They're a power station. Well, it used to be a power station, but now it's a data center. So they've hollowed it out, and they're using the size of power stations. So yeah, Google today, but it's going to be ubiquitous tomorrow. So this trend is happening all over worldwide. And so if you go inside these and you look at a server rack, this is important. This is the faceplate. This is the thing I said was terabits. You know, that's 10 to the 12. That's a billion bytes per second, right? And the most important part of this server is what we call these faceplates. Here's a faceplate. And the faceplate is important because that's where we plug in all the fiber optics. So you get all these yellow fiber optics, you plug into those faceplates. And you can see right now, there's not a lot of spare room there. I mean, the whole of the front of that server has connections. It's like having a hi-fi with no room for buttons, basically. And that's what it is, right? Lots and lots of servers with faceplates for ports. And if you start breaking that apart and looking at the technology behind them, well, the yellow is the single mode fiber that connects them together. You can see some of the yellow here. I've sort of drawn it schematically to connect these guys together. Now, the ones that are closer together use orange colored fiber, which is multimode, which I showed you earlier, which is a slightly bigger fiber. It goes less distance. It goes 50 to 100 meters. It doesn't go very far at all. The single mode goes quite a long way. I mean, the applications we're looking at, 200 meters to 10 kilometers, could go even further. And these black cables here, these are copper cables. These go about 1, 2, 3 meters. And so if you can get your technology scaled correctly, then you can have an impact in the single mode fiber connections here and actually start taking some of the market away from these guys here. And so you can actually start thinking about having single mode connections to take up some of this area here, which is very high volume. So single mode links will grow in volume and shorter distance. So if you can get the job done right with single mode fiber and the modulators that we're talking about, you start encroaching on other segments of the market. And you can see this in the next slide. This is our sweet spot. I colored it yellow because that's single mode fiber. And you can see on the vertical here, it goes all the way up to 50 gigabits per second. This is a slide that comes from Mellanox. And you can see the optical length. We're looking at sort of 500 meters all the way out to whatever that says, 10 kilometers, 10,000 meters. But you can see the orange, the multimode stuff, is in the sort of the 20 to 300 meter range. We do our job right, and we get our cost and our performance right. We start encroaching to the left, and we start encroaching to the right. So our actual opportunity grows. This is the sweet spot for our technology for polymer modulators is the yellow region. So this is a figure that Facebook has shown in public forums many, many times. This is how Facebook sees optical connections in their data center. And I won't even try to explain it because it's pretty complex. You can see there's just hundreds of different optical connections they've got in their architecture. I mean, it's pretty complex. In fact, what they say is, you know, hundreds of thousands of fiber optic links. So this is the way they think about their architectures. And in fact, I mean, they've also said, you know, 100G already today, near term we're going to see 400G. They're already thinking about 400G designs. They're even talking about 1 terabit designs. I mean, that's just way, way out there. But this is what these guys are thinking about today. So the users of the technology are driving huge volumes of optical interconnects with these types of architectures in their data center. So when they design these big data centers, it's not easy for them. They have pain points. They have challenges that they have to, we could call it obstacles, that they have to overcome. And I've tried to summarize these very quickly into 5 major areas. These are 5 big pain points, data center engineering headaches. So if you're an engineer in a data center, you've got to solve this somehow, especially as these data centers get bigger. To get bigger, you're going to have more single mode fiber. Obviously, they're going a lot faster, so they have to go 400G plus. They've got to figure ways to do that. They're denser. We've got to cram more stuff in a smaller space because now we're already looking at sizes of buildings that were power stations. So they've got to get it, and integrated photonics and packaging is really one vehicle where we can actually do that. They've got to make them greener. If you look at what some of these new data centers, they're right next to power stations because they're eating so much electricity. And I think I've read reports it's 2, 3, 4% of the nation's electricity are going into data centers today. That's a huge number. I mean, you just have to think about that for a second. And then they have to be economic. I mean, they can't cost a fortune. So we've got to get this metric of what they call is a dollar per gigabit, paying $1 for a gigabit of speed. That's the metric these guys talk about. We feel our Polymer Photonics platform is actually going to provide them lots of value. In fact, this slide shows you the classic, the orange multi-mode fiber that goes a couple of hundred meters. And today we're focusing on this single-mode fiber solution. We know the fiber can go 10 kilometers, so we can design the devices to go onto that fiber. We're nicely positioned. And so the takeaway of this slide is that if you're thinking about 100 and 400G, it becomes more ubiquitous using single-mode fiber. So you have to go this direction. Oops. So on this slide, going faster, well, this is a roadmap from the Ethernet Alliance, which is a standards organization that plots these metrics. And what I've circled here is these speeds where it's going to be the battlefield, and the battlefield is where 400G is. So the first companies to get to 400G are going to get a good opportunity of getting market share. And so this is the big battlefield that's happening right now. And it's going to be at 400 gigabits per second. So you're going to see this number come up and up again in my presentation. And so think about polymer photonics and what the technology is today. If you look at a laser today and see how it's packaged, you've got these types of classic packages. This is called butterfly package. It's a laser in here. In fact, the laser is this little thing here, and you see the fiber just coming through the wall. This is a pretty expensive way to package laser-type technology and transceivers today. And, folks are looking to try and go to integrated solutions, whether it's indium phosphide or silicon. You can see that they're trying to implement things on the chip. What we can do with our technology is we can do this with polymers. So we can certainly head in this direction and have a huge impact where others are trying to solve this problem and going there. We can do it with polymers. And so let's think about the denser part of the equation or the challenge, smaller footprint. This is a faceplate. So I took a standard faceplate you'd find in one of these data centers, and you add up the number of ports. This is where the fibers get connected in. Each one is a connectorized port for fiber. So you add them all up, and you get a total of 0.6 terabits per second. You're like, oh, that's a big number. That's 600 gigabits per second. So today, folks are designing 22 100 gigabit ports, and they really want 2 terabits. This is sort of where the state of the art is today. But you ask the customer base what they really want, that's not even close. They want 100. And they're basically saying to the tech companies, how do we get to 100? And it's not obvious to get any more sockets into this faceplate. I mean, it's pretty full already. So it's a tough technical problem when, you can't really change the size because the size is set. So you have to figure out how do we get more data through some of these ports. Well, you can make each one of these ports and the transceivers behind it faster. That's one way of doing it. Or you can come up with more innovative ways. But the takeaway is integrated photonics enables small boxes, so this has to happen by default. In fact, you're seeing this trend from larger boxes to smaller boxes. I just talked about the QSFP. This is a standard for the 25 gig QSFP. In fact, I'm even seeing folks designing faceplates with a hole in the front. This is a hole, and these green things are fibers. So they're actually putting the fibers all the way through. They just forget the ports, and they're actually going and putting the fibers straight down on the printed circuit board because they've run out of room. And so we have a real big problem here. So the faceplate is crammed, and fiber is now going on board, and I've got a slide. The next slide actually shows that over here. You see, they're calling it OBO, which is onboard optics. So the fiber goes through, you can see the fiber coming in, and it goes straight down to the board. Onboard optics via fiber connection through the faceplate. And of course, they've got to try and get these transceiver boxes smaller and lower power. So they're faced with all sorts of problems. And this is a great stage entry for our technology. And when you start looking at some of the economic designs required, now I know the numbers are really small, so I actually put some bigger numbers on the edge of the curve so you can see them. Today, we're really at 10 gigabits per second in the industry today. And what the customers want is 1. And so the trick is how do you scale from 10 today to getting to 1? And this is a linear scale, linear graph on the top. It's a log graph on the bottom. A log graph makes it easier to see where all the curves are bunched together. So you can, if you use a log scale, you can actually see a little bit more detail here. But you can actually, if Photonic integrated circuit technology is one of the vehicles can get to that metric the customers are looking for. And we can do polymer picks. So we know we're on the right vehicle in the right technology. So that's the key to achieve the economies of scale from today, which is 2017, all the way up to 2025. And so the next set of slides is, when you do that, you better look into the future to see what the forecast is going to be for picks, see where they're going, what are the areas, what are their challenges. And so I did this work 2.5, 3 years ago. It was 2014, beginning 2015, and I was at USC, University of Southern California, and we did some industry roadmaps for picks. And so the next 3 or 4 slides show you some of the roadmaps we put together. And there's lots of detail, so I don't want you to try and remember the detail, but just focus on these takeaways. Industry roadmaps help really understand what the customers want. And if you understand what the customers want, then you can design the technology to fulfill them. You can see there's a whole bunch of technology metrics on the vertical. 2015 to 2022 is what we did, right? So you can see lots and lots of detail, lots and lots of PIC type technologies. The 2015 roadmap focused on areas that needed attention. And I was the architect of these roadmaps. And if you get time to look at this afterwards, I don't think you'll see polymer mentioned on this roadmap because it wasn't on the radar screen. I wasn't even aware of Lightwave at that time. And when I was made aware of Lightwave by Fred, sometime in 2015, it was like, oh, wow, what an opportunity. And so with that opportunity, you start to rethink what the roadmaps may look like with polymers, because at the time, we weren't aware of it. We were looking at the classic technologies, which are indium phosphide and silicon. So in this slide here, what we noticed was up in 2018 and 2020, we saw these technology cost barriers. I mean, at the time, we sort of said, we sort of have the technology to figure this out, but we certainly can't afford it because it's way too expensive and it will never be implemented. So this is what we termed a technology cost barrier, and we colored those boxes purple. We called them the purple brick wall. And it's like, how do we get through these pain points? But from a USC's perspective, these are areas where we could focus in on the research. So it's like, oh, this is pretty cool. And so we said, oh, we can sort of take some of that technology and fold that in and try and break through some of these purple brick walls. And so in 2015, indium phosphide was the incumbent. Now it's silicon photonics. And by the way, I've now realized polymers have a huge impact on this roadmap. So as we went through the different slides, we realized, in the 2015 timeframe, optimizing technology and creating scalable solutions to achieve the roadmap goals, making sure the technology was scalable, and then taking that technology, driving it through those cost barriers so that we can get the solutions. And assuming we can do that, then we get to the hard-to-reach performance challenges, and that's where you really win with the high-performance stuff. And that's where it gets really, really exciting. So you're reaping the rewards by providing the customers with their wish, their high performance at their low cost. So, and So we have this living document, so we called it the roadmap, we updated it, and it just so happens in 2 weeks' time, maybe 3 weeks' time, there is a world roadmapping event in June in Holland, Bosch, and I've been invited to give a talk there, and it's my job to make sure that polymers are part of the next generation roadmaps, because they weren't before. And I think with what we've learned at Lightwave today, this is really exciting. So let's look at global markets. We did some estimates of the markets of all the photonic components in the datacom and in telecom arena, and these are big numbers. And so as you can see here, by 2025, this forecast, this is going to grow pretty steadily to $43 billion, where today it's running, it looks like about $20 billion. And so strong growth forecast in this segment all around. So this is a nice segment to be in. And I'll break this down into 3 major segments. In the communications, it's broken down into wide area networks, which is the green, as in access, which is in red, and datacom, which is in blue. And you can see 21 billion grows to 43 billion. And this is really nice growth for this market at a very high level. So we're playing in this market. Now what we also did is like, okay, it's great to have these numbers, but we're working on photonic integrated circuit technologies, PICs. So what are PICs going to do in this market? And what's this market going to look like in 2025 for PICs? Not necessarily polymers on its own, but polymer PICs, indium phosphide PICs, silicon photonics PICs. Where are PICs going to be? Is it really going to be integrated? And what we realize is 3/4 of this market is going to be PIC-based. And what that means is that the pressures to miniaturize these boxes and the photonics that goes inside them and to get extra functionality is so extreme that 3/4 of the market, or nearly 3/4 of the market, is going to be integrated by 2025. So that means if you're a tech company and you're not working on integrated photonics, it's not a good business to be in. You have to be into solving integrated photonic problems. And so this is what this slide says. PIC-based technologies become de facto by 2025, which is really exciting. And in fact, we looked at the data from a transceiver, a fiber optic transceiver standpoint, and you can see the $43 billion number there. And 58% of the market is going to be using transceivers. So transceivers is going to be one of the biggest photonic components in this marketplace from a communication standpoint. So there's very strong fiber optic transceiver growth over the next decade. So yeah, you've got to be able to integrate, and you want to participate in a transceiver play. And if you break that down, you break the transceivers down into more segmentation, you can see it's split into sort of 3 big segments of growth. Ethernet datacom, the green one here is wide area network, and the blue one here is DWDM. So the transceiver growth is driven by these 3 major segments going from 11 billion to 25 billion. And so if you look at transceivers and ask yourself, okay, so now we have the transceiver growth, what's going to be integrated inside these transceivers? Is it all going to be PICs or some of it going to be PICs? So we did some estimations here. You can see that this red line is the discrete components, and the discrete components are going to grow a little bit. They're going to flatten off, and they're going to slowly decline by 2025. But what's going to be inside these boxes? Wow, look at that. The integrated technology grows to $20 billion. It's huge. So that means most of the technology inside these transceiver boxes by 2025 is going to be integrated photonics. And so they surpass discretes by about 2021 or thereabouts. So have to be on that track. And so if you break that down into the segments, you can see 100G, 400G based technology. You can see the big segments here again, DWDM, wide area networks, and Ethernet datacom. And so they're driving the high-performance solutions. And this one's just showing it by market segment. If you show just the Ethernet by speed, because folks are interested in this speed metric, you can see here, there's a huge opportunity. It's called 100G, that blue color. And so that's going pretty quickly to, $4.5 billion market by 2025. But what's really exciting is if you can do that and you have the technology to do 400, look at the growth pace of 400G. It grows very, very quickly to $1 billion market. And so it means if your technology has the capability to go to 400, got to do it. It's a big growth area. And if you can do 400, you can do 100. So 100G is the main driver for big PIC-based technologies, but if your technology can go to higher speed, got to go there. So traffic is not the only application for integrated photonics. So I've just talked about traffic and datacom and telecom, but this is an interesting slide. This is medical applications. And if you think about it for a second, in the medical field, we have big microscopes and big boxes that are full of discrete optical components. These take up huge spaces. And a lot of the medical profession want handheld types of medical devices. They want battery powered. They want everything miniaturized. They want to be able to walk to where the patient is to do the analysis. And so integration enables miniaturization. So there's a huge interest in miniaturizing, in this particular slide, optical coherence tomography. The next slide, the same thing for cytometry and detection. If you took a cytometer today, a flow one, look at the size of that beast. That's like 3 meters by 3 meters by 3 meters. I mean, it takes up a whole room, and you probably have to have your own air conditioning. What these guys want is an integrated chip, and they're demanding that. And so if you have the facility to integrate photonics, then you have the technology to sit down and talk to these guys and say, how do we do this? So integration again enables miniaturization. Same thing for spectroscopy. You've got these big units here on the top left, and they want to go down to handheld units on the lower right. Big trend today. They want battery operated, they want handheld. Same thing for endoscopy. I mean, today we can, some of us can swallow these little cameras. They have an LED and an image sensor in, but they want more intelligence. And so miniaturization is going to allow a lot more intelligence into these units, where you sort of wireless all the signals out, and you can see what's happening on the inside. And so we're going to see a lot more applications for this coming down. And also, I mean, there's other applications too, like military, which I haven't talked about, medical, I talked a little bit about, in defense. So there's broad opportunities for PICs outside of those billion-dollar numbers I talked in traffic and communications. Pretty exciting. So let's talk about our platform. Polymer PICs. Now, last year, and I think we talked about this data that we achieved in our polymer materials, our percominions family of chromophores. I mean, they're very stable, they're very reliable, so I think most folks in the audience may have seen this data before. We're really happy with this data. This is making us really excited. So using this technology, using our polymer materials, we can start thinking about some of these types of applications inside a polymer photonics integrated circuit. And of course, the modulator is the first device we're looking at today, but there's others too. And so, you know, we've got polymer photonics, and if you look at this sort of curve of where technologies are today, we're the green one, we're in the center. But on the left is one of the incumbents, indium phosphide. As we know, indium phosphide can do the laser, can do some photonics functions, but it can't really do electronics. And so, so if you've got an indium phosphide solution, you still have to use a silicon IC chip. On the other end of the scale, most people have heard of silicon photonics. You can do a lot of things in silicon. You can do the ASICs, you can do the electronic chip, you can do drivers and TIAs, transimpedance amplifiers, you can do some modulator designs, but you can't do the laser. What we find is that polymer photonics can work with either technology because it's a spin-on technology. We can spin it on to either. In fact, if you look at some of the building blocks we're looking at here, right now we're looking at the modulator, which is this guy here. Now we know we can't do a laser, we can't do a semiconductor optical amplifier, and that's understood, it's a polymer material. But what we can do is once we have the light, we can modulate it, we can direct it, we can split it, we can combine it. So we can do a lot of things with the light. So we can build a library together to work with a lot of different platforms, which is pretty exciting. This slide here shows the polymer impact that we've done some calculations internally on 100 and 400G type systems. And you'll see numbers here, the impact, the cost improvement impact, depending on how you design your different transceivers, could be as much as 40%. And so we know we can add an impact to the bill of materials in the transceiver design. And so this is making us really excited. And so we're starting to look through different competitive bill of materials and seeing how our polymers will have an impact there. And this is sort of the first set of data, and we're going to actually improve this data as we go on. So the takeaway is polymer economics drives effective scaling in transceivers, and we're seeing some really nice numbers come up already. And the curve I showed you before, this is a similar curve. You can see folks are at 10 gigabits, $10 per gigabit today. We know we can hit these curves with polymer technologies down to 1. So it puts us on a confident track that we can scale our technology. We can scale it in increased performance, in higher speed. We can also scale it in lower cost, which is what the customers are looking for. So driving increased performance with our platform. This is what we did the press release with in December, the Ridge Waveguide Modulator, and also the press release in April. And so this is just a cross-section of what it looks like. We have a core, and then we have the cladding on the outside. No different than what I showed in the earlier slides and the tutorial side part of the talk. This is a Ridge Waveguide polymer structure for high performance. And so I showed you this little cartoon of the modulator earlier. You put in the data into the modulator and you get nice clean data out. We're right now optimizing the parameters to increase the performance. For the bandwidth going from 10 gigabits per second to 25 gigabits over the past 6 months. So you've seen a lot of technical progress in the company in the last 6 months. And of course we have to focus on these types of metrics to improve the performance, the drive voltage, the insertion loss, the size, the yield. So even though we've presented nice results, we've still got engineering work to do. But we're optimizing to create a customer-ready modulator. And I think this is a mask set of the modulator designs. And so this is the mask design of various modulator layouts that we have in our evaluation of different devices internally to fine-tune the performance. And I believe on the next slide is an actual picture of a modulator. And so you can see the schematics on the left-hand side for a multi-gigabit design. And this is a photograph showing you the gold bond pads, and we connect the electricity to the modulator, and the light's going through down these tracks here. It's pretty small, but this is the RF design is critical for high-speed modulator design. So we're actually making these Ridge Waveguide modulators today. And this is the slide that shows you the 10 gigahertz data. And so this slide where I've circled here on the left-hand side shows you the frequency at the bottom that we plotted the data, and at 3 dBs down below the data we know we have the bandwidth and the operational performance for 10 gigabits a second. And this was the slide that generated the press release back in December. So we're pretty excited about that. So this is modulator performance on 10 gigabits per second. And we actually did a lot of background experiments. These are electrical graphs showing you plotting a lot of data, matching it to simulation, seeing that we have similar data with different lengths of modulators in those 3 graphs. And this particular graph showing that, I've drawn a red line here showing that we have greater than 10 gigabits capability, which made us really excited in December. So then it's like, okay, if we can get greater than 10, can we get to 25? And that was a real challenge. And so internally there was a lot of excitement to do that. And in fact, this was the press release that we put out in April. This is data showing that we have 25 gigabit capability. As you can see here, it's not very clear on the resolution, but this is 26 gigahertz. And so we have a Mach-Zehnder modulator that now can enable us to get into the 100G market, because you gang 4 of these together, 4 25s to get to 100. This is what everybody's doing. So now we can actually access that big opportunity I showed you in the marketing slide. So that's really, really exciting. So this data shows that we've clearly got a 25 gig modulator. And now we've done some modeling. So this graph here is not data. So this is simulation. This is working on the computers and doing modeling and trying to figure out how fast these guys will go. And you can see from this here, so it's simulated modulator frequency response. And so these 2 red arrows pointing down, that was the first press release showing that we've got 10 gigabit capable modulator. And then we did the 25, which is this guy here. And this dotted line is really this dotted is because we're not there. But we can see from our modulating standpoint that we could get to 50. So we've modeled it, we've simulated it, and we're pretty comfortable with some good engineering internally over the next year. We should be able to get to the 50 gigabit area. And if we can get to 50 gigabit, and you gang 8 of these guys together, so that's 8 times 50, now you can access that 400G opportunity. That's huge. And that puts us right at the very front of the technology companies. We're ahead of everybody then. So, yeah, it's not going to be easy, but we've seen internally we've got the designs, and so the job now for the engineering team is to demonstrate that. And so when you go back to this type of architecture, here is where the modulators sit, and so we'll have a laser behind them, and we'll be using them for high-speed signaling. And so we're really excited that we can really sort of push the technology even further. And so the question is once you push the technology further, are we going to do everything on our own? No, we're not going to do everything on our own. We're too small. There's other players out there who have got better skills to do better things. Like, for example, we want to be really good at doing modulator designs and making an engine. It's what we call an engine, which is putting this engine on an optical subassembly. But should we get into this, what I would call the box business of transceiver modules, there's already 20 companies out there that can do that in their sleep. With big factories, with big capitalization, have raised all the money. That's not our skill base. Our skill base is the polymer technology and making sure it works at 25 gig and pushing that to 50. And so this is what we're focused on, is making sure this engine is unique, adds a lot of value to the customers. But should we get into this business, I think we should partner to do this business. This is the key thing. We should partner to do that. I think I showed this matrix before. And so what this looks at is what everybody has and what people would like and what we can offer. And we certainly can offer a 400G solution using our polymer modulator. That's pretty exciting. Now, we're not there yet, but we've seen from our simulation designs internally that we have a good chance to get there. Oops. We went forward. Maybe we'll go forward. And so what are the advantages of polymer modulators? Well, we know we have high electro-optical efficiency. We know we have low power, low insertion loss, a small size. These are really cool attributes. We've got the potential to get to 50 gigahertz. That's really exciting. If we get to 50, we get 8 of them together, we go to 400. And that's really exciting. We've got robust material. We showed that in high stability, high operating temperature. And we know the material is compatible with photonic integration. So this is really exciting. And so we know our Mach-Zehnder modulator platform is capable of being very, very competitive in the marketplace. Now, I haven't talked about slot modulators because last year and the year before we talked about slot modulators. So we haven't forgotten about slot modulators, but we have focused on the ridge waveguide. We still are working on slot modulators, and this is the slide I said before. And right now we're actually talking to a partner to work with on slot modulators to increase the performance in a very similar fashion to what we're doing with the ridge waveguide. But I don't have any data to report at this meeting, but only to say that this is not forgotten. This is still being worked on, but we can't work on everything and focus on everything. We have a small team, so right now we're going to focus on the ridge waveguide. But with the slot, we're actually working with a partner to help us along on that. Because we don't want to be hiring lots of people. We want to keep the team small and focused and world-class. So the slot is going to go forward, but we're going to be working with a partner on this. Polymer resurgence. There's a lot of interest in the last few years in polymers. Now, I said when I did these roadmaps in 2015 and late 2014, wasn't on the roadmap. We weren't even thinking about that at USC. But now you look around, you see lots of interesting papers, a lot of universities are working on it. So this technology is actually coming back with a resurgence because people now see that it's scalable in high performance as well as low cost. And this is what the customers of the data centers are looking for. So probably one of the most important parts of this talk is what are our technical plans, because I know there's going to be a lot of questions on this. So what are our plans? Well, what have we achieved first? So last year when Tom got up, he talked about, getting March 16, getting the polling sorted. And so as we worked through last year, we actually achieved the 10 gigahertz ridge waveguide bandwidth on time by the end of last year, and you saw the press release, so we're really excited about that because we executed on time on what we said. Same thing, we started realizing in January, wow, this thing can go faster, we could push it to 25, started working really hard on that, and by April, we got 25 gigahertz demonstrated. So that was another press release we saw, so we were really excited about that. And so we achieved what we wanted on plan, on time. So that was really great to see. The team has come together and we're actually really producing great results. Now at the bottom, I don't know if anybody's read this, we want to get to 50 gigahertz EO bandwidth by the end of this year. That's our goal. If we can get to that, then clearly you put 8 of them together, you can access that 400G market. So we're really focused on pushing the technology even further. In fact, on this slide, I'm showing it from a 12-month perspective in 2 areas, one on the technology platform and one on an operational platform. On the technology platform, this is 12 months. We want to complete development and characterization of the first generation package modulator. So we want to put this modulator into a package and operate it at 25 gigs. And in order to put it into the package, the lowest risk way to do that is to partner with a packaging company. And I'm here to say that we signed a contract with a packaging company. I'm not going to name them at this point. We're on track to do that. So we're pushing forward to actually take our modulators, put them in a package with a packaging company that's very experienced. Now why are we doing this? It's because it's a low risk way to do this. It's much easier to do that than actually hire packaging engineers and build a team and buy an equipment. It just makes a lot more sense to do that. So that's what we're going to do. And once we have that, we're going to conduct reliability testing because we can do that. That makes a lot of sense to make sure these things are reliable. In the meantime, the engineers are going to be pushing this 50 gigahertz bandwidth by the end of the year. So really pushing that technology forward. And then, some of the things I'm going to do is make sure that all of the polymers are now on the world roadmaps. They weren't 2 years ago. They are going to be this year. And we're going to start off in Holland in the next couple of weeks. And then, clearly, once we get them packaged, then we'll be in a position to talk to customers and provide samples to customers. And so from an operational standpoint, clearly in order to do this, we're going to upgrade our materials and our facilities. This has to happen. We're very small facilities. I'm not expecting huge, but we're going to have something a little bit bigger. And we're going to continue to build a world-class team, and this is happening as we speak. And so this is something we're really going to be proud of. And we don't want a huge team. We want a small, focused, world-class team that can design 50 gigahertz devices. So it's going to be a high-value team. Clearly, we're going to have to file more patents because now we've got a new platform. This is not just polymer materials. This is polymer materials used in devices. So we now have to think about filing patents on the devices and the PIC side of it. So you're going to see a lot more patents get filed. And then, clearly, we're going to have to update and increase our testing and characterization laboratory. So we're going to have to start measuring these devices at higher speeds. We don't have the equipment yet. So we're in the process of buying more test equipment so that we can measure these high-performance devices. So is this exciting? Yeah, this is really exciting. So if I can be here in a year's time and show that we've completed all of this will be pretty cool. And so what I did this time is I think everybody's seen the roadmap that Tom produced a couple of years ago that I think is on the website. So we're in the process of updating the website. So this is the new product roadmap. And it's used the same basis as what Tom used, except I used red, orange, green, or red, yellow, green behind the boxes. And red is indicated of development. Yellow is qualification, reliability. Green is product. And you can see we're in the bottom left-hand corner right now with a 25 gig ridge waveguide modulator. And what I've written in this box is optimizing parameters for package prototypes. And that's sort of where we are today. So we've got the 10 and the 25. But we've got to march up here to the top right because where we'd like to get to is 400. And the way you get to that is you've got to have a 50. If you have a 50 device and you put 8 of them together in an array, an 8-channel, then you can access the 400G market. So that's the direction we're going. This is the product roadmap. So a couple of slides on closing notes before I lose my voice here. If you look at competitive technologies out there today, indium phosphide is the incumbent. It's out there, it's been used for a few years, a lot of the big companies are using it. But it's not as cost effective and it's really struggling with the performance. And so there's a chance to actually displace some of that. Folks may have heard of a new challenger, the silicon photonics. A lot of companies have been talking about this. This has certainly made a lot of progress. A lot of big companies are using it. It's still, the jury's still out to say if it really will become the incumbent or not, but it's certainly a new challenger. And our challenger is polymer photonics. And we think not only are we a new challenger, but we're actually symbiotic with both of these guys. We can work with both of these guys. And so this what makes our technology even more exciting. So in terms of summary, well, we know the internet's going quickly because my kids are never going to use less data. We know that, right? So that appetite for data is still growing. There's new applications enabled through miniaturization, not just in traffic and communications, but in biophotonics, medical, and consumer. We know integrated photonics is going to become a major technology platform. PICs are going to be key for data centers, especially at 100 gigs and beyond. And we expect polymer photonics to become a key platform in the PIC scenario. And then in terms of what we see, we actually believe at Lightwave that polymer photonics is here to stay. We already showed 25 gig performance. And we already know now that we can access this huge, explosive 100G market opportunity with a 4x25 solution. And we've done some internal modeling, simulation, calculations, if you like, and we know we can push it to 50. And so the last word on this technology and this subject is actually from 50 years ago. And it's a movie, and I think most people have seen the movie The Graduate, Dustin Hoffman's first major movie, all right? Mr. McGuire, I want to say one word to you, just one word. And Dustin Hoffman, who plays Benjamin, yes, sir? Are you listening? Yes, I am. Yes, I am. Plastics. Exactly how do you mean? There's a great future in plastics. Think about it. When you think about it, well, of course there is. Thank you.
Is this on? Yeah. Okay. Give Michael a chance to recover his voice and also for you all to formulate some good questions. It's also not very often an opportunity that a Navy lieutenant has an opportunity to take the microphone away from an admiral. So when the opportunity presents itself, you seize the opportunity. I thought it might be interesting for you as very loyal shareholders. You've been very patient over the years, very supportive. Thought it might be important for you to get some of the board members' perspectives on Tom's tenure as CEO. And Tom and Jim, over the last few years, have made a wonderful leadership team. Tom has brought to our company a direction and focus that we had not seen before. If the team wanted to work on 25 different things, Tom would say, pick one or two and get them done. As those of you who have been in organizations know well, there's a great deal of difference between management and leadership. And Tom has brought leadership to this company. He's gotten resources that evidenced by Michael coming into the company, Fred coming on our board, and the talented team we have in the back of the room. The board comprises a broad range of skill sets, and Tom has found a way to bring that together. It's a group that works very well together. In fact, we all like each other. It's a good group, a lot of leadership. Right now, I would say we are in what is a seamless transition. We're ready to make the next step forward. Tom and Jim have brought us to where we are today with a lot of great effort. Now, Michael and Jim are ready to lead us forward. It's a seamless transition because Tom has agreed to stay on as our chairman, and we look forward to Michael and Jim taking us forward to the next level. It's great to have somebody who's got a worldwide reputation lead us into this very next important step. So, Michael.
Thank you.
Congratulations.
Well, thank you, Bim. That means a lot to me. We put our heart and soul in this, and I'm going to continue to do that in every possible way. So, it's really been an honor for me, and I look forward to going forward. What we'll do now is just open it up to questions. And if you can, we have a microphone, Steve, if you can do it. And for the people in here, Steve will hand you a microphone. Please raise your hand and identify yourself and then what we'll do is I'll kind of direct the question to the appropriate person. So with that, we'll just go. So we'll figure it out from here.
Hello, my name is Alex Cherubin. I'm currently interested to know how many companies are interested in your technology right now?
I would say, I don't know the actual answer to that, but I think what's actually happening is through our press releases and through some of our talks at conferences, a lot more people in the last 12 months are aware we're around, we exist, we have technology, we're not just doing polymer materials. I think we're being watched by a lot of companies right now. And do I know exactly how many? No, I don't know exactly how many. What I'm actually focusing on is actually making sure that technology is working to a level that's going to get them really excited. And so I think the right strategy right now is not actually knocking on doors of other companies and saying we've got this great technology, because we're not finished. We got some results that look really, really exciting. And our job right now is to make sure we get all the I's dotted and the T's crossed, so that when we engaged, it's going to be a very simple decision for the customer base. And that's the trick.
Michael, I'd like to add something to that. As many of you know, over the last 5 years that I've been CEO, I've talked about the interest of potential partners. And last shareholder meeting, and even the one before, what I had discussed is there were a handful of what I would call, the greens, the let's go kind of people. When Fred started getting involved, and along with Michael, Fred and at that time was an advisor. We have Siraj, who obviously is very technically astute in all this, and Michael started advising me to let us get to a next level before we re-engage, because I've talked to dozens and dozens of these companies. And, I have to trust the people with the technical background to understand what it's going to take to really get people excited. I think we're extremely close, but, I've already done this with Jim multiple times. We've opened a lot of doors, and they're waiting, okay? And they're waiting for us to re-engage with them. It's now up to the technical team now and the new leadership team to make sure that we can get there. I'm absolutely convinced, when Michael and the team achieve the 50G thing, we're not going to have to open many doors. We're going to have to bar them closed so that, we can pick and choose where we want to go. But
that's true, yeah. You want to develop your technology so that people start coming to you. And so the trick here is understanding the technical nuances of what the customers are looking for. And if you can show you can do that, then you don't need to knock on their doors. They'll just come here. And so over the next 12 months, you saw that plan. It's a pretty stretch, challenging, exciting plan, but we think it's doable. And I think it will answer your question. People will know when we're getting close. I mean, they always do. So we're known because I'm a fairly public person in the community, and so is Fred. As they see our press releases and our talks at conferences, we're going to as Tom says, I don't know about barn door closed, but certainly it's going to be a lot easier to talk to many different potential customers.
Hi, I'm John Rooney. When you get to 50 and ganging the 50s together to go to 400, is there a gating issue there as far as size and power?
There's not a gating issue per se, it's just a tough technical challenge. And so if you look at what's required today is, what's the easiest way to explain this? We went from 10 to 25 in 6 months. And the difference between 10 and 25 is smaller than to go from 25 to 50. Because what actually happens is, as you go up in frequency, you become more microwave. So the best way to explain that is, on a silicon IC, you have a gold wire bond, a little wire that connects it to a package. Now down at the 5 gigabit or the 10 gigabit level, it's a wire bond. It's a gold wire, but it's a very thin wire. But at 50 gigs, it's an antenna, just like the aerial on your car. And so it's not just a simple wire bond. It doesn't do the same things at high frequency. So the device pads have to change in dimension. The thicknesses have to change. The whole design has to be different. So it's more tricky. And so I think to answer your question, it's not just power. Power is certainly one of them. But we see the potential performance to get there. And once we've got the 50 gig bandwidth demonstrated, then we're going to focus on the other parameters. And we're pretty confident we can do that.
Dick Haskell. I've got 3 questions, and if you could answer them, first about the 25 gig device, and then about the 400 or the 4 by 25 to 100. First, when, if you can tell us, when you hope to have a package prototype in the hands of potential customers so they can do whatever they're going to do to it, approximate time frames. Second question, when you have talked about the sizing of markets, what unit pricing are you using to size markets? In other words, are you using $10 a gig, or are you taking the price down? And then lastly, for each of those devices, if you could tell us what the size of the market potential that you see for those 2 devices.
Oh, so well, the first one was in the slide, so let's go back. So the first question is when we can have a packaged device, right, in the hands of customers. Well, the 12-month plan says provide samples to customers. So we want to get devices out to customers within 12 months. We don't have packaged devices today. We just, I guess I've just announced that we're working with a packaging partner, and so we're working on that right now. And as soon as we have devices that are adequately packaged and the performance meets our expectations, then we can check with customers and see if they can test them.
Well, it may be helpful to explain what it takes to make a package, on the devices, because I'm sure they don't know, just in a 30,000-foot view.
A package is an environmental protection box around your device. So you have to package all devices, whether it's a laser or a photodetector or a modulator. And so you have to get your electrical signals in and the optical signals in and out. And so in an IC chip, when a silicon IC chip is packaged, you actually put it in a plastic package or a metal package and you wire bond it to big legs, and then the legs connect to the printed circuit board. Same thing with this, with the modulator. So we've got to put our polymer modulator, our ridge waveguide, the 3 layers, into some type of box and provide electrical connections so we can provide power and provide fiber so we can get light in and out of it. So that takes some time. And, we're going with a low-risk option of working with an established packaging house in order to do that. So we just started that process.
Is there an expectation relative to putting together for ultimately getting to 400 gig from about a number of years?
The package design will be capable to take 50 gigs. So assuming our devices go that speed, because we're not there yet, then we'll get there. And the second question, remember the second question.
The dollar size of the market, and when you're sizing those markets, what's your unit price per gig?
So you saw from those graphs, I mean, the numbers that you're seeing today in the marketplace are 10 gigabits, $10 per gigabit, $5 a gigabit, that sort of range. And so what I did is I looked at the average selling price of products today and then forecasted that. And in essence, they're not going to make it. And so if you really want to get market share, you've got to beat the expectation of the forecast. And a lot of those curves I showed, they start off at 10 and they go to $2 or $3 per gigabit, but the customers want $1. And so
Can the competition hit those numbers?
I don't. I mean, it's hard for me to say what the customers are doing, behind closed doors. What I've seen from my experience is that the competition is having trouble meeting those metrics. And so that puts a lot of emphasis on us designing our technology that is really scalable to make sure it does get there. And so, whether our competition will get there or not, I couldn't really say. What I do know is they're having problems. This is really tough. And so if you've developed the technology and you're already down the path, to redesign it for even higher scaling and lower cost is difficult. We're just starting. So we're starting on this track, 6 months ago, 10 gigabits, 25 gigabits. We've got the advantage of we know what the customers want already. So we're designing that scalability right into our technology platform, right at the very beginning. And so that's really exciting. That means that I think we're much better poised to meet those metrics than some of our competition.
I think the question is, if you have no competition,
Nobody else will be able to hear what he's asking.
why price our technology down to what they want versus what the market
Exactly.
And Michael, because he's not speaking in a microphone, can you just repeat the question because the people that are remote can't hear what.
Oh, right, sorry.
That's not,
So the question was about price points. And just because the users want to pay $1 per gigabit, should we sell at that? Absolutely not. We don't want to leave money on the table. But I want to make sure that our technology has the scalability so that when we're out in the marketplace, we can price so we make sure we can maintain our margins, where our competition may not be able to maintain their margins. So I think that's probably your question.
I'm Sean Doherty. I'm just trying to get clarity on, so it seems like you're comfortable with the 25 gigs and going to doing a device with 100 gigs and you're beginning a partnership with someone to build that box. What I'm not clear on is when you're talking about, obviously the 400 gigs is is the apex where you really want to be. Is there an interim strategy to be dealing with, it looked like there was a huge 100 gig market. Is there a strategy, in other words, it seems like it's incremental. You don't have to get to 400 to start selling stuff, 100 gig market. And so is there a clear strategy on breaking into the 100 gig market? And if there is, you're partnering with someone, they're building a box, and you talked about within 12 months getting into someone's hands.
So let me
go ahead.
So if you looked at the plans, so we're going to do the 25 gig, we're going to package it, and we're going to do reliability on it. And assuming everything looks good, we're going to customer sample it. Customers are going to give us our feedback, and at that time we can make a decision on how we want to move forward from manufacturing that. And then most likely we'll probably look at somebody to manufacture the boxes and the transceiver side of it, and we'll focus on the engine. But I want to get to that point. In parallel, we're going to push our technology to show, because when we sell 100G2, they're already looking at 400. They're already, so even if we go and sell 100, they're going to say, well, where's your 400? Where's your development for your 400? They expect that. And so you have to do both. So we're pushing really hard to get the 25 gig packaged, evaluated, with reliability, out to customers. First question they're going to say is, before they write any PO is, so where are you on 400? So they want to see a coherent strategy from 100 to 400 and beyond. And so if we don't, so let's say we take your question and we say, we just do 100, we take that market, we don't worry about the 400, customers not going to be happy. They want to see that we can upgrade our technology to 400 too.
And to the extent that there's a huge market right now in the 100 gig market, and maybe a lot of those producers can't get to 400 either, but they're using the producer's 100 gig box, you guys can produce the 100 gig box, I imagine, at a cost advantage. And so going to your last point about we can't get to 400, but there's this huge 100 gig market to be tackled, and we can do it cheaper. Is there still the ability to play in that market even if you didn't get to 400?
Yes, there is.
Okay.
It's just, I want to do both.
My name is Michael Corcoran. I have two questions. The first one would be, do you plan to continue to use Lincoln Park Capital as the primary source of financing for the company? And the second question would be, do you plan to move to a different exchange in the future within this 12-month period?
These are not technical questions. So the answer to the first question, I'm actually going to hand to Jim.
Well, we have a 3-year, 36-month agreement with Lincoln Park Capital. We've raised about $2.6 million with them, and we have it's available to us another over $17 million. We try to do it wisely. We have a lot of warrants out there on some of the private raises that we did in 2014 and 2015, and just since the close of the last quarter, we've raised over $500,000, $502,500, just people exercising their warrants. So that's another avenue. That overhang's already there anyway. We're going to take full advantage of that. So, and quite frankly, from everything we've looked at in the alliance or going over alliance agreements that we've had with Lincoln Park, it's been very inexpensive money. So.
The second question on the exchange.
Oh, well, yeah, I can.
Well, I think did you have another question about the Lincoln Park?
My question for my follow-up would be that Levy's connection to the industry, if you're looking for more influential or relevant finances for tech is a business. You were adding to capital.
Yeah. Yeah, so I have a lot of connections in industry, and both on the technical as well as the technical finance side of it. But as of right now, the resources we're receiving from Lincoln Park is fine for the team. I'm not sure that's necessary to go out and raise more money right now. We certainly have a very small team. It's very focused. We're picking up world-class engineers as we speak. It's not going to be huge, and we're not looking to spend tons of money building big factories. So this is really going to be a very high-performance, high-frequency design team that can actually design these polymers for lots of interesting applications. So as of right now, I think we're okay. But if we need to use my Rolodex and talk to some of the high-tech companies, yeah, we can certainly do that. Just give it to me.
I think the other opportunity, Ron Bookey from the board, is we want to. I think as a board, we're always sensitive to dilution. And what impact will a new money raise be on our existing shareholders? And we have a lot of longtime shareholders who have really believed in this company, and we don't necessarily want to go out and get a venture capital firm or new money raises that will significantly, have a dissolution effect on our shareholders. And we have the opportunity. Lincoln has been a great partner of ours right now. It's worked out the way we intended it to and the way we've hoped to have it. So at this point, there really isn't any reason to change that. We're still attracting, world-class scientists and people and have the ability to continue on. And Jim manages the money very prudently, and we're not a spendthrift organization. And so I think currently everything is going well, and there's no need to change it.
And not to pile on, but I will. And that's that, I know where you're going. And, the potential there with these partners is that they would want to then start investing, right? So that you don't have to go to banks, you don't have to go to Lincoln Park, you don't have to go to whoever. But packaged advice is absolutely required. So once we get to that point, then Michael can unleash his fury on all his buddies that are, that exist in the worldwide market, not just the U.S. side of the house, and really try to leverage that to help finance the company to go to the next level. Does that help? Okay. And Jim, market? Up market?
The other thing we constantly do is take a look, and we're looking at for his uplisting, okay? And we take a look at the requirements, if you will, for uplisting. We want it to happen naturally. We have different options, obviously, different levels, both NASDAQ and New York. We watch those very closely, but we want it to happen in a natural, organic way, right? I.e., we're not out looking to do reverse splits just to uplist, okay? So.
Yeah. While people are thinking of any other questions, I do want to correct one thing from Michael's presentation. You should never do this in front of everybody, right? But he had something wrong. In one part of that, he said, everybody has a smartphone. I can guarantee you Dick Haskell does not have a smartphone.
He told me he was getting one.
Steve, can you look and see if we've had any questions?
At last I looked, there were really no questions of any relevance.
Okay.
And
all right.
We did such a good job on the presentation, and we've answered everything.
Any other questions from the group here? All right. With that, we will call the meeting adjourned, and all the directors and employees will be staying around. Oksana, I'm sorry, did you have anything you wanted to say? Okay. No. Like I said, the board and our employees will be around. Don't ask them for inside information; they won't give it to you. And so everybody knows we're required. The board is required to have a short meeting here to ratify the minutes of this meeting. So please give us just literally a couple minutes here to do that. And once we're done with that, we'll be around, and you can ask any questions to us there personally. Thank you very much for your attention.